So I want to talk about the Runge-Kutta method. So we have a second order and a fourth order. The fourth order is a little more involved than the second order. It's going to be a little more accurate than the second order. RK4 is actually going to be more accurate than Euler's or improved Euler's also. We are not going to do this by hand, but you can see the formulas that are involved and how this is going to work. So we are going to do this exclusively in Excel. So to do this, we need a few columns. We need an X column. We need a Y column. We're going to need a K1, a K2, a K3, and a K4. So notice that I've got the differential equation. We're going to do number 10 first. That way we can compare it if we wanted to improved Euler's, since that's one that we did improved Euler's on. So we can compare answers. We did not do Euler's with this one. We could go back and create a spreadsheet to do that. They do give us an initial condition of 0, 1 on this one. And they want us to find 0.5, and we're going to use a step size of 0.1 to do that. We're going to set the spreadsheet up, however, so that we can change that step size to anything, and it will just kind of filter through the formula. We won't have to do a whole lot in here other than maybe drag formulas down if we need to increase x to 0.5. So our initial value is 0, 1. X's are going to increment by 0.1. So we're going to say equals. It's going to be that previous x plus the x here. And I have put all my x's, that increment, in H1 for all of these spreadsheets. I'm going to drag this down. So we're going to have to compute some k values first. Let's go back to our formulas. So to find K1, we need to evaluate at that xn, yn. So I'm going to put that in here. That way all of my xn, yn stuff is in that same line. So the formula is equals. It's this x value plus this y value. Just kidding. X value times that y value. I'm going back to the differential equation here. X times y plus square root of y. So plus square root of y. So there's our K1. Let's look at K2. The formula for K2 changes just a little bit. It's the differential equation evaluated at x sub n plus half the step size, and then y sub n plus half the step size times that K1. So it's going to be equal to, it's this evaluated at x plus half the step size. So plus our step size divided by 2. Okay, so there's my x value. Now I need to multiply that times the y value. Our y value is going to be that current y plus half of the step size times K1. And notice I'm having to put all that in parentheses because it's really just x times y for the first piece. So our y is, I'm plugging it into this y. It's y plus the step size divided by 2 times K1. So y plus half of the step size times our K1. So this says the x times y in this format. Plus, now we got to do the plus square root of y. So plus square root of y, and our y was all of that fun stuff. So I'm just going to copy that piece in. Some of the features here. Hit enter. So I'm going to click OK. I've got something wrong right here. That dollar sign belongs in front of the 1 there. Hit enter. So there's our K2. And like we said before, we could highlight that column and make this bigger, and you're going to see more of those decimal places. So K3. Here's our K3. It's a differential equation evaluated at x sub n plus half the step size, y sub n plus half the step size times K2. So equals our x formula in this case. Remember, it's x times y. Our x formula is going to be x plus half of the step size. So you could do 0.05 times the step size or the step size over 2. Either way. Lots of ways to do it. So there's our x value. Now let's talk about that y value here. We're going to multiply these together. You do have to put the multiplication sign in. Excel doesn't realize it's multiplication unless you type it in. So it's y sub n plus half of the step size. So I'm going to do step size divided by 2. Times our K2, our previous K. So there's our y. So we've written x times y. And then we got to do plus square root of y. So I'm just going to recopy that y formula again. There's our K3. Now we've got to do K4. So K4 is going to go the whole step size amount instead of the half step size amount. So X would be this column and row, that cell plus our step size times Y. Our Y is going to be B3 plus the whole step size times K3. So that's X times Y plus the square root of Y. Just going to copy and paste that Y. Enter. And we get that. So we've got formulas for X. We computed K1, 2, 3, and 4. Now we need the formula for Y. So here's our Y formula. It's that previous Y plus 1/6 of the step size times K1 plus 2K2 plus 2K3 plus K4. This guy is a weighted mean of those K values. It's weighting K2 and K3 a little heavier than K1 and K4. So this is equal to y sub n. Notice this is not using that differential equation, it's using the values of k1 through 4, and these values use that differential equation. So it's y sub n plus our h divided by 6 times k1 plus 2 times k2 plus 2 times k3 plus k4. So now I'm going to copy all the formulas down. And we won't see what's supposed to be down here until we copy everything else. So then our final answer for a step size of 0.1, y of 0.5 equals 1.75609. And if we wanted to see more decimal places, we could make this column a little bigger, and you'll see more of those. So likewise, if we were to change this to 0.5, we could, but we would have to carry all of these formulas down. I mean 0.05, not 0.5. You can see how all the formulas are changing as we carry them down, because it's now able to compute what's in those blank cells since there's something in there. So then our final answer would be that. So just for fun, let's compare this to that last one. I'm going to take a picture. So this is using RK4. I'm going to move this picture over here. And then let's go back to that improved Eulers. So improved Eulers gave us a value of 1.755997. RK4 at that same step size gave us 1.756. So RK4 is always going to give you a better estimate. Or almost always going to, I can't think of a place where it wouldn't give you a better estimate than Eulers or improved Eulers. So just for fun, let's do one more. Let's look at this guy. So I'm going to bring the formulas back up so we have them side by side. So we need columns for X, Y, K1, K2, K3, and K4. And I've already typed the differential equation in. And we have an initial value here at 0, 2. So that's our first X and Y. We want to find Y of 0.5, and I'm going to use a step size of 0.1. So this is H equals 0.1. So we need a formula for X. So we're going to do equals X plus that step size. I'm going to go ahead and drag this guy down. So now we need that K1. K1 is evaluating the differential equation at the current xy. So our differential equation is 4 times x minus 2 times y. So equals 4 times x minus 2 times y. K2 evaluates the differential equation at x plus half the step size and y plus half the step size times K1. So this is going to be equal to 4 times x, but our x is 0 plus the step size over 2. And then it's minus 2. Now we're back to that differential equation times y. And our y is going to be the current y. So it's going to be 2 plus half the step size times K1. K3 is equal to 4 times our x plus half of the step size minus 2 times the y value. So our y value is right now 2 plus half of the step size times K2. So this says 4 times x minus 2 times y. And then our K4 is taking the differential equation and evaluating it at x plus the whole step size and then y plus the step size times K3. So for us, it's going to say 4 times x. Our x is this 0 plus the step size minus 2 times y, and our y is going to be the y sub n plus the step size times K3. So we have our formulas for K1, 2, 3, and 4. Now we need it for y. And y is that weighted mean. It's y sub n plus the weighted mean of the k's. So this is equal to that previous y plus the step size divided by 6 times K1 plus 2 times K2 plus 2 times K3 plus K4. So if we were to filter all the formulas down, our final answer is 1.10366, and that's at a step size of 0.1. And like we said before, if we wanted to, we could change that step size, adjust how long these are, filter the formulas down, and then we could get an even more accurate answer. The smaller the step size is, the better the answer is going to be.